So before we begin, Ayush pointed out that this should have been 2n minus 1. This is the number 4. And actually in the proof it's okay, but in the statement it's wrong. It's q raised by 2n minus 1. Okay. So, so today, let's see, might do some easy stuff because, um, something went wrong with my tooth. I had to run to the dentist, and the dentist took forever, so I didn't get a chance to prepare. So I decided that about the parts that I didn't prepare, I'll just present something from a some basics of a current piece of work which I'm doing. But we'll do a couple of theorems at least. So anyway, recall the following. We had so this was k, and this was the generating function of p of n. So these were paths basically. So you're going to this point mk. So each part is less than equal to k. No, they're k parts. Sorry. So partitions of n with k parts. This is k parts, or less than equal to k parts, and each part less than equal to n. So this set of partitions generated will give you this guy, right? So this was the largest. This part gives the largest part, and this is the number of parts. And basically, you have a path going from 0, 0 to m comma k, and you take the squares above that. So that's the partition. Okay, and we in lecture 2, we had done a recurrence relation for this. So in lecture 2, we were looking at this parts actually, but by symmetry, it's the other part. So for some reason, we were looking here because we were looking at inversions, but we can do above the path, and this is what we got. So the proof was very easy. So this we had done. We had done from here a formula which was QQN, QQK, QQN minus K. So if you expand it out and you cancel this part, this was 1 minus Q squared after 1 minus Q raised by N minus K. No. Write it here. The first few terms cancel, so 1 minus Q raised per N minus K plus 1. 1 minus Q raised by N minus K plus 2, and so on up to 1 minus Q raised per N, and 1 minus Q squared, so on up to 1 minus Q to K. So this was the formula we got, and based on this formula, we also had M choose K, Q is equal to N choose N minus K. So there was a symmetry, right? So now what we do is we add, well, we can do one theorem straight away if we want for this, but well, let's just add, let me add, add a parameter. So generating functions with one more parameter. another parameter, counting number of parts. This is also very common that we have something with k parts, for example. So we can count the number of, so minus zq q sub m, which is uh, j going from 1 to m, 1 plus z q to the j. So if I expand this out in powers of z raised per k and q raised per n, then I will get partitions of n with k parts. And in this case, there'll be k distinct parts, right? And each part is less than equal to m. And so this will be a sum over k equal to sum over n and sum over k. Where the 0, 0 term is just 1. And similarly, one can have 1 over 1 minus dq to the j, and j going from 1 to m. So this is a strange thing. It's not going from 0 uh, here. Of course, it doesn't go from 0 because otherwise you'll get a. So you're allowed to go 0 here if z is not there, but I mean z is there, but even so, we just go from 1 to m. And this is again over n and k. If you compare the coefficients of z raised per k and q raised per n, you'll get normal partitions of n with each k parts, not necessarily distinct, but each part is less than equal to m. So n and k going from 0 to infinity. So you have you can use the, I mean, essentially the same idea as earlier for generating functions, except that we use um, an additional parameter z to keep track of the parts. So for just for an example, what we are looking for is if we just take 1 plus zq, 1 plus zq square, sorry, this will be 1 plus zq plus z square q square plus zq q cubed, so on, multiplied by 1 plus zq square plus zq raised to 4 plus zq raised to 6 uh, square cube, and so on. So when I multiply various terms, I'll multiply, um, you know, so this means that I'm taking uh, two parts equal to one, right? And this one will mean I'm taking three parts equal to two. So when I multiply both of them, I get this z raised to 5, which keeps track of number of parts. So that's where the k parts comes from. Is that clear? Is that okay? Is that fine? Please give me a sign of life. I think we did this Q binomial theorem. I'm not 100% sure. 1 plus. Well, it'll be m, but I mean, we can write infinity if you like. It'll be, I mean, here it's the largest z can go is m. So k going from 0 to infinity doesn't make sense, but anyway, we assume everything else is 0 otherwise. So this is this, and so I'll just put a brackets. here. It helps to think of it as infinity, but it's mm, k plus 1 over 2 and n choose k, 0 is per k. So this is the theorem which we'll prove. Um, okay, so this is I mean this is a polynomial on in Z, so it goes only up till n, but it helps to just think of it as infinity, and it helps to think that n choose k, q choose k is 0 for k bigger than n, and that's indeed that is that's just a convention. So, yeah, so how do we do this? Well, this side we know is a generating function for partitions of n with distinct parts less than equal to k and no part bigger, all parts less than equal to n, right? And this is z raised per k, q raised per n. And this is only on k, and here that means that whatever I have here, this n part has been summed. So for some fixed k, that number of parts. So how do we get that? How we get that is as follows. Color, color, color. Okay, let's try this guy. So, so what I do is I add 1 plus 2 plus 3. This we've done before up till k. So this is 1 plus 2 plus 3 up till k. So this is a partition of uh, k into k plus 1 over 2. And to this, I add a partition which is fitting into a. This fits into a, let's say this is k parts and this is m minus k parts. So this is generated by this guy. I mean, whenever I have nothing here, it means q in any case. Okay. So this is fitting in here, and then you attach it to this chap. And what this chap does is it makes sure that the attached thing is a distinct partition. So now this object, which is this whole thing, this object's the generating function is exactly q raised per k plus 1 over 2 times m choose k, right? And this object is exactly the guy with, for fixed k, it's the generating function of all partitions where of n where they're distinct parts, they're k distinct parts, and each part is less than equal to n. Overall, this is m minus k plus k. So overall, this is going to be less than equal to n parts, right? So that proves it. I mean, then this is you sum over all k's. So summing over all k is this generating function of all this guy, this chap here, q raised power n. That should give you this chap.
Oh, Professor.
Yes.
Oh, Professor, can you please repeat what the MK factor contributes on the right hand side? Like what? Like is the M minus K cross K rectangle completely filled or
No, no, no. It fits within it.
okay?
So, I mean, just a reminder, if we have something like this, right? So then I can have, so this is 1, 2, 3, and then 1, 2, 3. So 3, 3. So then I use this guy. So it's because I can't put a rectangle, a square above it. But if I have this chap, then I use this guy. So if this is the path, then I have a complete thing. So same here, same issue here, that you could have this guy, and then the rectangle. The only Ferraz diagram is this chap, just this box. So it's less than equal to k and large less than equal to m, and then that is m plus k. Choose k because you remember you're choosing k out of kx's with m plus k totals 0 1. Remember this binary thing. So the number of paths was m plus k. Choose k because we chose k once from a total string of length n plus k. So this was the story. Okay, any doubts on this proof by pictures? Any issues here? So yeah, I mean, some it's difficult to explain in words what it means. Essentially, the generating function of this guy uh, is exactly this by means of this picture, this bijection. So there's a bijection between partitions of this kind attached to this kind, two distinct partitions. So there's a one should say that there is a bijection of this kind with partitions with k distinct parts. Exactly k distinct parts, and each part less than equal to m. Sorry, say that again. Okay, so all right, so we are done with one theorem, and I have another one. So this is the second Q binomial theorem. So this is in our notation, it is ZQQM, and this is equal to, now this is really a series, Q raised per K, M plus K minus 1, K, Z raised per K. And this is, you need both these guys. Well, you don't need this much. Yeah, you do actually. Because there is QZ. So anyway, so you need this for convergence of this guy. And how do you prove this? Well, this is, recall, this is the generating function for n and k and q raised per k, q raised per n and z raised per k. And what comes here is partitions of n where less than equal to k parts, and each part less than equal to m. So this m comes from this m right here. So we are making it finite in one sense, and then from what we did earlier, and then we have to sort of fit the partitions into a smaller box. And how do you get less than equal to k parts and each part equal to m? And here there is exactly k parts, right? So what you do is you take any partition of this kind, you take any partition of this kind and you split it into, and suppose it has k parts, so you split it into this k and then the rest, whatever you fit in. So this is less than equal to m plus k minus 1. So overall it will be m plus k parts. Overall it will be less than equal to m in size and minus k, I think it is. I'm wondering whether this should be minus or plus. Um, no, I mean, there's one more part here. So it's m plus k. This is fine. So this has, this part, let's say, has less than equal to k parts. And this part has less than equal to m plus k minus 1 parts. So the overall, this guy has less than equal to, so it should be m minus k. Because, yeah, what am I getting here? Why am I getting m plus k? No, then I would get just m. So this is fine. This side, this is fine. Each part should be less than equal to m. Is that right?
Yes, Professor. I think it's correct.
Why is the m coming in? Well, yeah, I mean, okay. So this is why we had the m plus k over here. We're going till here. Yeah, this is fine. Yeah, unnecessarily got confused. Okay. So this is fine. So overall, the number of parts are m plus k. No, right? There's some slope here. I don't know what. This should be m minus 1. Maybe. Ah, that's the problem. Ah, now it's fine. So one part here and one part here. And this is what confused me a little bit, but this is the correct one. Is this right now? I think this is right. We want overall m here, but then we have m minus k plus k. Yeah, this is okay. Overall m plus k, yeah, this is okay. All right, so this is a bijection of all partitions of this kind. Of n with exactly k parts, and each part less than equal to m. Right? Because there are m minus 1 here and one more over here. And those are counted exactly by this chap and this chap, so they're equal. So generating function, this is the, so this is the generating function of these partitions of P of n, where k parts, each part is in. So this is equal to summation n q raised to n. And then now summing over k, we get the result. So, okay, so let's just step back. What we've done is we've got this kind of this thing written out as a power series over here, and n, sorry. And you could so this is one of the finite forms of the Q binomial theorem, so-called Q binomial theorem. And we've also got this guy written out as a. This is also Q binomial theorem for sure, because Q binomial theorem is something like 1 plus z raised per n, and this is something like 1 plus z q 1 plus z q square. Yeah, n. So if you put q equal to 1, you will get this guy, and then whatever you are getting over here is obviously q equal to 1, you will get this. And this is also an infinite type of Q binomial theorem. And in fact, there's a most general Q binomial theorem is essentially of this kind. You expand this as a power series. So maybe I may give them exercise on this. So you can, I'll just write it down so I remember it. So I'll outline Ramanujan's proof. Okay, so that's good. Any questions on this?
Professor, just a small question. So I got the part where we get the generating function for like exactly k parts with each part less than or equal to m. So how do we go from there to the summation?
Yeah, so this is a generating function. So it is so it's equal to p of whatever that partition q raised per n and summing over n,
Right,
and this should be m maybe. And so you got this particular term is a generating function, is a sum over n, and this is a sum over n and k. So this is the just the if you take out n and just sum over k, so you'll write all this stuff z raised per k, and then you will sum over n, right? This is a double sum. So what you have inside this guy is essentially this guy. This is what we have proved.
right.
No, this is not what we have proved. What we have proved, what we've got is something like this. So this p q raised per n. So this part is a generating function, which is this guy over here. And then when you sum it over z raised per k, then you should get the whole sum. So yeah, so the right. So here, this is not right. What we are looking at is you're taking n inside and summing over that, and then getting some answer. And this is being counted by partitions, which is to be expected. I mean, the q part is the part which is to be. Does that clarify stuff?
Yes, Professor.
Okay, so yeah, the next one is there's an identity we did earlier, and it's a finite version of that. So this is I don't know who it belongs to, but anyway, um, this is n choose j square. Okay, so when q equal to 1, this is an old identity which you must have seen in 11th grade. So this is the Q version of that. So in fact, Q analog. So it's a Q analog of this guy. How do we prove it? So we go from um, 0 to n. So, so we go all the way, and whatever this partition is, well, the better come. So this is 0, 0. So whatever the partition is, let's say it has a Durfee square of size j here. So this is a j by j thing. Then something here and something here. And this will be um, so this part is less than equal to n minus j. This point is nn. This part is less than equal to n minus j, and this part is uh, j. So we get basically n choose j as a generating function. This is the generating function of this part. This part is j on top, and this is n minus j. So this is generating function of this is n minus j plus j over n minus j. And generating function of this guy is q raised per j square. So q raised per j square, n choose j, n choose n minus j is the generating function of all partitions in this box, in this n cross n box, right? With um, yeah, with Durfee square of size j. So summing over j, we get all partitions in this box, right? So we get 2 raised per j square, n choose j. And now we notice that this n choose n minus j is also n choose j. And this is 2n choose n. So this is of course your, almost your Catalan number. So since n choose n minus j is equal to n choose j. So this is j square and then n choose j square. I mean, I forget to write the q's. If I forget, then you write them yourself. Or we should just ignore, we should say that let n choose k be the same as n choose k with a q. Wherever you see either one, it's the same. Okay, so that finishes the proof. It's again simple proof by pictures. Any questions? All right, so um, this is a finite form. We take n going to infinity in this. So you notice that the top part is on this part. So you take limit as n going to infinity of j going from 0 to n. This is actually going to n. So I don't know why we're doing infinity, but it's actually n. Q raised per j square. And this is qqn square, qqk square, and qqn minus k square. And this is equal to qqn QQM. So formally, we get j going from 0 to infinity, q raised by j square. So these two will cancel, and you get 2q. The k, sometimes it's a k, sometimes it's a j. Usually I put k's, I don't know why I did j. And this one of these cancel, and you get q infinity. So this is formally, and to um, so what do you use to justify interchange of limits? Since you've done calculus analysis, please tell me, how do you justify the interchange of this limit with the sum? I think there's a Weierstrass M test, or there is a dominated. This is my favorite convergence theorem. It's much easier to apply. Yeah, so I mean, basically, you have to show each term is bounded by a convergent series, and it's a real pain to do that. Okay, but you show that it's bounded by something like this, basically, very similar to this guy, and then you prove it. So, or you don't bother justifying and just do it formally. Okay, so I mean, if you've implemented it till n up till this is j, no, this is n. If you've implemented it up till n equal to 1000 or 100 or whatever, you get a sense that this converges for any particular value of q. It's quite fast convergence actually. So these products are in general convergent faster than sums. Okay, any queries? Any questions? Are you there?
Yeah, no, Professor. Professor, the cancellation is happening because we are taking limits as n tend to infinity and the products become the same, right?
Yeah, yeah. I mean, beyond a point, it's convergent. So both are convergent. So it just goes to this. But there is a problem with this sum. I mean, rest everything is okay. This sum is an issue. Okay. Let's start a newish topic. This is what I said, that I ran out of things to prepare because I have to go to the dentist and there's a limited time. So then I'm going to show you another thing, which is okay. I mean, this is also, I plan to do it in any way. Okay, so this is an approach to enumerate partitions, and this is again joint work with my uh, friend Satosh Bhatt. So I'd ask you to Google him. Did anybody Google him? No? Okay, so my suggestion is Google this guy. It's an unusual chap doing mathematics. So, uh, so his full name is Hatosh Singh Bhatt. Okay. Yeah. So let's look at this statistic. Let fk lambda. So let lambda be a partition. Let fk lambda be the number of k's in lambda. Okay. And let capital Fkn be the number of k's in all partitions of n, i.e. The number of Fk lambda for lambda partition of n. So this notation you've seen, right? This says that lambda is a partition of n. So let's do a counting now that you've done it. So, I mean, when I'm working on this project, every day I begin with this. So, so you add one to each guy here, right? Add one here. So you get 4x1, 2x1 plus x2, x1 plus x3, and then you can add 2 now to this guy. So it's 2x2, and then you have a new one, which is x4. Let's do 5. So I hope you programmed this, right? I'm used to x1, x2.
Yes, Professor.
So 3x, no, x1 plus 2x2, x1 plus x4. Then x2 plus x3 is a new one which comes in here, and x5. So 1, 2, 3, 4, 5, 6, 7. Right? So let's just keep track of nk of n. So where k is here, there is nothing. And k is 1, so there is number of parts uh, which are, so it just counts the number of ones in the partitions. There's just one here. Counts the number of ones here. So there are 2 ones here. 3 here plus 1, 4. Okay, 4 ones here plus 2 ones, 6, 7. Right? So how many are here? Can you count and tell me? So 5 plus 3, 8, 10, 11, 12. So this is k equal to 1. So this side I have got nk of n, and this is k equal to 1. And write it above. So k is 1. And k is 2. Okay, so this is 0. This will be 1. This will be, how many 2's are there? 1. How many 2's? 3. Then how many 2's here? 1, 3, 4. Yeah. Okay. No 3's here. Number of 3's here is 1. Then number of 3's here is also 1. Number of 3's here is 2. About 4. 1 here. 1 here. 5 is 1 here. All right. So you know what this thing means. So first of all, notice that what is um, k times fk of lambda. What is fk of lambda? Fk of lambda is number of, so in this one, number of ones in lambda. So if we're just sticking to this lambda, let's say, number of ones in this lambda, so I'll multiply 1 by 2. This is the number of ones. And then number of 2's in this lambda is 1, and I multiply by 2. This is really a it gives me what is n. So this guy, so in this example, it is equal to 4. This guy is n clearly. I mean, this is just you're just counting in a partition of n. You are counting the number of k's and you're multiplying by k. So you're counting k plus k plus k. You know how many times it comes. So you're really count adding up to n. Is that clear? Is that obvious? Is this fine?
Yes, Professor.
Okay, so now what I do is I sum over all n, over all lambda, this guy, and I sum over all lambda, which is a partition of n. So I take all the sums over partitions of n. So here what am I getting? I'm getting k times fk of n, and here I'm getting n times p of n. So because, number of lambda basically. So this is a fundamental kind of identity which you get immediately from when you start considering this. Fine. So let's call this done. Now, what we want to do is the goal is to enumerate partitions, and what we do is we enumerate these f's also at the same time. So the next topic is what we do is we give a recurrence relation for f's. So what am I doing here? How do I get the one here? I add an x1 to this guy, I add an x1 to this guy, I add an x1 to this guy. So I add an x1 to all these guys and I get these are the new ones, new x1s which are coming. So it's clear that f1 of n is you take each partition of n and you add a 1 to each one of those. Each one of these you add a 1, x1 to, and then whatever ones are already existing there, those you add up. So is this clear? I'll just say obviously. Is this obvious to you? Please give a sign of life.
Yes, Professor. Makes sense. But it's only for one, right?
Yeah. So now how do I get twos? What I do is I add an x2 to two guys previously, and I will get something, right? I add 3x1 plus x2, x1 plus 2x2. So whenever I have an x2 here, I can subtract 1 and go to this guy, right? And then whatever 2's exist over there, oh, sorry, this is n minus 1. So it didn't make so much sense. So the previous guy I'm going, and here I'm going 2 steps back, and then I count all the ones which were already there. So what am I doing? Suppose I want these, count these x2s. Yeah.
Professor, sorry to interrupt, but I had network connectivity issues over the past minute, and I couldn't follow anything after you said recurrence for F. So if you could please quickly repeat that.
Recurrence for f's. Okay.
Yeah.
So fine. So what do I do to get an x1 in this row? What I do is I multiply everything in this row by I add x1 to everything here. So I add an x1 here, I get 4x1, I get 2x1 plus x2, x1 plus x3, right? So this gives me 3 new x1s, and then whatever x1s existed there, those are already there. So 3 already I've got new ones, which are, from these set of partitions, plus 4 are already there, and overall it becomes 7.
Right. Okay. Yeah. Makes sense.
So f1 of n is p of n minus 1 plus f1 of n minus 1. And similarly, f2 of n is p of n minus 2 plus f2 of n minus 2. So what I do is I add x2 to 2 steps previously. All these partitions are at 2 steps back, and I add an x2, and whatever x2 existed, they are over here, right? So this is pretty good. And you can keep going on to Fnn is P of n minus n. And there's nothing there, but you could write. There's no n's at the zero state, but you can write this, right? So this is true. Fine. So now what do? We subtract this on this side, so we get from, let's call this a, f1n minus f1n minus 1 is equal to p of n minus 1. And then I sum. So I do f1n minus f1n minus 1 plus f1n minus 1 minus f1 of n minus 2 and so on. And here I get p of n minus 1 plus p of n minus 2 plus 1. You keep going. In the end, you're going to get, zeros on both sides. So you get f of n is equal to p of n minus 1 plus p of n minus 2 and so on. Yeah? Okay, I mean, what this one, sorry, f1 there. And similarly, you have f2 of n is, you get, what do you get? You get p of n minus 2 plus p of n minus 4 plus p of n minus 6 and so on. Fk you will get, yeah? Is
So,
that okay?
Professor, won't
Yeah.
the sign for Pn on the right hand side alternate?
Mm, no, you're bringing f2 on this side and then you're summing. So you bring this fk on the other side and then you sum. So this side will all be pluses. Here it alternates and then it cancels.
Professor, because oh, okay, so
I mean, don't think too much about it. We just bring f1 on this side and then we sum. And this side telescopes and you get the sum over here.
yeah,
Pn
yeah,
minus. And then you just do p. The second guy will have pn minus. So you bring this over here. Suppose, let me just do it in green. Fkn minus Fkn minus k equal to p of n minus k. Now I iterate it. I say, okay, Fk of n minus k minus Fk of n minus 2k is p of n minus 2k. And so I go in steps of k and cancel everything. And at some point, I'll just get Fk in here. And here it will be n minus k, n minus 2k, and so on. After some point, they become zero. So we of course, we know that Fk of n is zero for k bigger than n. So there is no part equal to k bigger than k bigger than n in the partition of n. So this is true, and we know that this is zero also. So both sides will stop at some point, and you'll get this. Fine. Okay.
yes, Professor.
Okay.
Professor,
Yeah.
there's a Stirling's theorem also, right? Something along those lines, which say like regarding this, which says that the number of ones. It says something about the number of ones occurring in all partitions of n,
Yeah.
right?
Yeah. We'll get to that. That is called Stanley's theorem. Yeah.
Stanley's theorem. Sorry, yes, Professor.
Yeah. Yeah. We will. So that was direct motivation for this guy. Okay, so anyway, you got a system of equations, right? Now you guys are such kings of um, linear algebra, I heard. So how do you write it as a matrix equation? So you write it like this. I mean, this guy continues till fnn right? P of n minus n. And over here, uh, write it a little bit downstairs. So f1n, f2n, so on up till fnn, and there's this matrix. And then here, if you notice that it starts with n minus 1, then n minus 2, and it goes on till p of 0. And the first term is 1, 1, 1 everywhere. The second term starts with n minus 2, and then it's n minus 4. So it's this. Third term will be, do you see that? This is p of 0. So you get it in there. So this is the matrix equation. So let's call it A1. Let's call this A, this matrix A. And this is equation A1. And this guy, you can actually write down the ijth entry. So it's 1 if I divides j and 0 otherwise. Right? So every term, so start with 1, and 1 divides 1, 1 divides 2, and so on. Here 2 divides the second term. So in I divides j, so the jth column, second, fourth, sixth, and so on. And similarly the third, sixth, and so on. Is this clear? So let's call this equation 1, and this, let me call equation 2. Fk of n is equal to k Fk of n is equal to npn. And let me call this equation 3. This is a starting. Now these three equations determine Pn and Fkn for all n k. So what's happening here is, so let me do an example. You understand this? This we did just now. We did this right here. This is our star. And there's an initial point we have to begin with somewhere, that is P0 equal to 1. So what happens is, if you notice on this side there is n minus 1, n minus 2, and here it's n. So let me do some examples. Okay. So for n equal to 0, you have P0 equal to 1, right? So for n equal to 1, you will write F1, 1 is equal to this matrix, which is just 1, and P0. So this will just give you 1. That means F1, 1 is equal to 1, right? Now, what are we saying? We are saying, so this side is determined. F1, 1 is determined. Now, from this equation, let's determine P1. Because for the next one, I need P0 and P1. So what is P1? P1 is 1 times F1, 1, which is equal to 1. So P1 is determined, right? Now we can try F2. So F2 of 1, F2 of 2, this should be equal to this matrix, which is 1, 1, 0, 1, and P1, P0, right? So it's a triangular system. So what does it tell? I mean, just multiply it. It tells you this is 1. Let me just write this equal to 1 and this equal to 1. So 1 plus 1, that's 2. and 1. So that will give me f2 of 1 equal to 2, f2 of 2 equal to 1, right? And uh, 2 times f2 of 1, what was it? K times,
Oh, Professor, we'll get f of f1 of 2 and f2 of 2 instead of f2 of 1 and f2 of 2.
yeah, yeah, yeah. So this is the confusion. Yeah, so 1 times 2. So what I want 1 times fk of times 2 plus 2 times 1, which is equal to 4. And this should be equal to 2 times p of 2. So that means that p of 2 is equal to 2. So I get p of 2 now. All right. f1 of 3, f2 of 3, f3 of 3 equal to this matrix. Now I have 2, 1, 1 over here, and this matrix. So 2 plus 1 plus 2 is 4. This is 1. This is 1. So f1 of 3 is 1 is 4. f2 of 3 is 1. f3 of 3 is 1. And 1 times 4 plus 2 times 1 plus 3 times 1 should be equal to 3 times p3. So this is how much? 6 plus 3, 9. So p3 is 3. So do you see how these three things determine all of them? You don't know anything. You don't know P0, okay? You don't know F1s. You just know this matrix, and then it determines it. It enumerates it, right? It tells you the number of Pn. It also tells you F1k, F2k, and we can verify. So you can see 411 we calculated, 21 we calculated. Okay, is that good? So now, what are you okay with this? Is this fine?
Yes, Professor.
I mean, this is brand new stuff. Actually, we haven't published it yet. I mean, it's kind of trivial, so we can't publish it as it is. But nobody apparently has looked at this. This is a number theoretic matrix, right? So nobody has looked at it before us. But anyway, we're getting a lot of stuff from here, all in this elementary fashion. Um, and I mean, I would have done it in the class today. I just did it because. Okay, so now Ayush mentioned the theorem of ASCII. So what ASCII of Stanley. So what Stanley was looking at was this guy. He was looking at F1 ones, and he noticed that if he says, so let's take this guy. So he says number of ones coming in the partitions of n is equal to the number of terms which are repeated uh, at least once. So here in this partition, x1 is repeated at least once. In this partition, x1 is repeated at least once, x2 is repeated at least once, and in this partition, x3 is repeated. So all these guys count and they become 4. Okay, so this is Stanley's theorem. So Stanley's theorem is, I'll write down the things properly, but first this one.
Professor,
Yeah.
Isn't it like if we have, so we have 4x1, right? So
4x1.
x2 is one time, x3 is one time, so that's two, and maybe if we count x1 as one time, so that is three, right?
No, no, we count x2 also. X2 also comes in a partition at least once.
Okay, so x2 is one, x3 is one, right?
Yeah, and
So that is
x1 is also one here, and x1 is also at least one here. At least one.
okay.
At
Okay.
least once. So number of times a part comes at least once. Okay, so that is for F1. Now somebody also noticed about this guy. So here is 2. So F2 we know it is the number of times x2 comes, right? And now you count the number of parts which are repeated at least twice. So x1 is repeated at least twice here, x1 is repeated at least twice here, x2 is repeated at least twice here, that's 3. So this also matches that. So, so here's the story. So this is known as Stanley Elder Fine theorem. So somebody's mic is making noise. Shivam, yeah, can you switch off your mic? Okay, so here let's call it gk of lambda is the number of times um, the number of parts which appear at least k times in lambda. So this is like suppose we have 3x1 plus 2x2 plus x3 plus 4x4. Okay, suppose this is lambda, and suppose we want g3 of lambda. So number of parts which are appear at least 3 times. So this will count this guy and this guy. So it will be exactly 2, right? And let gk of lambda be equal to summation gk of lambda for uh, lambda partition of n, gk of n. Okay, then the theorem is, and this is actually due to Fine, but rediscovered by Elder, and Stanley did not even discover it. He put it as an exercise somewhere. And then he said it's probably well known. He didn't check, and then he found it in a paper of Elder. And recently they found it in a, somewhere in a paper by Fine, Nathan Fine, and they called the paper a Fine rediscovery or discovery. So that's very interesting. Anyway, so the theorem is that Fkn is equal to Gk of n. And we have 10 minutes, so let me prove it. Okay, you understood the theorem? So this is the keyword, at least k times in lambda, and then you add up all those guys, and then you should get the same. So it's kind of like Hall's kind of theorem, but very subtle. It's not sort of clear why it's like Hall's theorem. So we show, we know Fkn satisfies the recurrence equation of kn equal to p of n minus k plus p of n minus 2k. So on. We show gk of n also satisfies this. I mean, it's not a recurrence, it's a formula. Satisfies the formula. And people haven't even written it like this in some for some reason. Satisfies. Okay, so how do we prove GKN also satisfies? So let's just look at it this way. Suppose we are adding. Um, so suppose we add x1 to each partition of n minus 1, and we add 2x1. That means repeated twice to each partition of n minus 2. And we add 3x1 to each partition of n minus 3, right? So each, uh, you know, uh, what are we adding? We are adding 1 plus 1 here. We're adding, you know, 1 here. We are adding 1 plus 1 here. So each partition of n, basically, this accounts for, in each partition, it accounts for something, some partition which is repeated at least once, right? So, am I doing this? No, I don't think I'm doing it right. What I should do is I should add x2 to each partition here, x3 to each guy. So here we are adding 2, here adding 3, and so on. So, I mean, I'm writing x1 for 1. So you add 1 to each partition of n minus 1, 2 to each partition of n minus 2, and so on. And in this way, each part which is repeated at least once is counted by this. And we need to, right? So it should be clear that g1 of n is equal to p of n minus 1 plus p of n minus 2. So, again, going back to this, what we are saying is that if we have here's x, here's x1, here's 2x1, x2, 3x1, x1 plus x2, x3, 4x1, 2x1 plus x2, x1 plus x3, x4, and 2x2. So I'm at this level. What I do is I add x1 to each guy here. I add x2 to each guy here. Okay, if I add x2 to each guy here, 2x1 plus x2, it will add to, this part has already been counted because I've added x1. But this part was not counted. So this x2 gets counted. Similarly, if I add x3 to this guy, x3 will get counted, and so on. So if I do all this stuff, then I will get all the parts, the number of parts which are repeated at least once. And one can do the same with G2. So for G2 of n.
Oh, Professor,
Yeah.
could you repeat that argument, please? I didn't quite follow. How is each part which is repeated at least once counted?
So I'm adding 1 to each guy here.
Right.
So one of the x1s, which is repeat, one of the x1s in each guy, this one x1, this x1, this x1, is all counted in this. Now I
Right.
add x2 to this guy. So then this part will get counted. Add x2 to this, then this part will get counted. It has to be counted only once. This x2 only accounts for 1. I mean, it contributes 1 to this gk. It is a part which is counted at least twice, right? So this is what I do. Here I just add an x3 and this one is counted. So basically I'm counting this guy plus this guy plus this guy. This is what I'm doing. So each time I'm accounting for one of the x1s which are repeating at least once, one of the x2s which is repeating at least once, and so on. So this thing, think about it, it's quite obvious. So G2n, what we do is to add G2n, we add 1 plus 1 to each partition of n minus 2. I add 2 plus 2 to each partition of n minus 4. So I'm adding 4 to each partition of n minus 4. I will get a partition of n which has at least x2 repeated twice, at least x1 repeated twice, and so on. So G2 of n is equal to G of n minus, sorry, P of n minus 2 plus P of n minus 4, right? And similarly, if I want to calculate Gk of n, so I'm adding 1 plus 1 plus so on up till k times. I'm adding 2 plus 2 k times to every partition of n minus 2k. And when I do that, I account for a part here, this 2, x2, we account for that x2, which is repeated at least k times. And notice the at least, because, you know, here 1 is added, but it's at least 1. So if it was already there, it's okay, it doesn't matter. It's still counted once. Okay, so it's the same thing. I can bet you this is the simplest proof of this. They go into a little bit of nuts trying to prove it, but you know, it's a classical theorem. So, I mean, our interest is to get some more generalizations if we do it by this way. Okay, so I think that's time's up. This is enough for today. Any queries?